Section 7.4 is titled Division Properties of Exponents. What we want to make sure is that by the end of the lesson you can use the division properties of exponents to evaluate and simplify expressions. So the first property is called the Quotient of Powers property. What this states is that the quotient, remember that's division, of two non-zero powers with the same base equals the base raised to the difference of the exponents. So if we have a to the m over a to the n, notice that the bases are the same, they're both a's, then we just subtract the exponents, the top m minus the bottom n. For our example, we have 6 to the 7th over 6 to the 4th. Through subtraction of the exponents, 7 minus 4, we get 6 to the 3rd. And when we multiply that, 6 times 6 times 6, we get 216. And let me show you why that works. Remember, with multiplication we add, but with division we subtract. So if we use the example down here, 6 to the 7th is 6 multiplied 7 times. 6 to the 4th is 6 multiplied 4 times. What occurs here then is we have 7 6's on top and 4 6's on the bottom. We can start canceling some of those 6's, similar to how you would reduce a fraction. So we get 1, 2, 3, 4 6's that will cancel, because that's the most we have on the bottom, and that leaves us with 6 to the 3rd on top. So you can see why subtraction works. So let's look at some examples. We want to simplify. Number 1, we have 10 to the 12th over 10 to the 4th, and that's going to become 10 to the 8th when we subtract 12 minus 4. But because this is a number raised to a power, we do want to multiply this all the way out. And remember, we learned in our powers of 10 that when you have 10 raised to a power, it's a 1 with 8 zeros. So that would be 100 million. Example 2, we have 2 to the 10th over 2 to the 5th. So when we subtract the exponents, 10 minus 5, we get 2 to the 5th. 2 to the 5th, remember, is 2 times 2 times 2 times 2 times 2, 5 times, which is 32. In example 3, we have 3 to the 10th over 3 to the 7th. If you want to pause the video here and try to solve this one on your own. But 10 minus 7 is 3, so that's 3 to the 3rd power, or 3 times 3 times 3, which is 27. Now let's look at some examples with variables. The rules here don't change. We're still dividing like bases, so we're going to subtract exponents. On number 4, we get r to the 2nd power, 9 minus 7. Number 5, remember you want to be careful. The exponent on the bottom is a 1 even though it's not written. So we're subtracting 6 minus 1, getting n to the 5th. On number 6, looks a little funky, but we have h to the a over h to the b. We have like bases in the h's, so we need to subtract the exponents. But because they're variables, we can't actually get a number here, but it's h to the a minus b. Seven, 8, and 9 get a little more difficult because we have more than one variable in our numerator and denominator. And what's important to remember here is we treat each variable separately. Also, you'll see in example 7 we have coefficients, and coefficients need to be dealt with just like they would in a fraction when you reduce. So on number 7, let's look at the coefficients first. We have 6 on top and a negative 2 on bottom. Well, if I just wrote 6 over negative 2, most of you would be able to reduce that to 3 over 1. You can keep the negative sign in the bottom, or you can bring it back up top, or you can put it out in front. Remember, we talked about negative fractions, how the negative symbol technically can really be put anywhere. I'm going to go ahead and leave it on the bottom since that's where it was in the problem. Now we have a's to deal with. Well, on top we have a to the 1st, and on bottom we have a to the 1st. A to the 1st over a to the 1st. We do 1 minus 1, and we would get a to the 0. But remember that a to the 0, or anything to the 0 power, is just 1. I won't have to write that 1 since it's multiplication, but essentially what's happening is these a's are canceling each other out. Then for the b's, we have b squared over b to the first. That's going to give us b to the first. Now a common question is, how do I know when I write it on top or when I write it on bottom? Well, when you subtract, notice we had more b's on top. That means that the b, the variable, will actually remain also in the numerator. Whenever you have more of a variable in the bottom, in the denominator, then that's where your answer will end up. And we'll see that in an example here in just a minute. So the final answer is 3b to the first, or 3b, over -1. That's just me cleaning it up a little bit. Example 8, we have 8b squared c cubed over a c squared. So again, we have a to the first over a to the first. Those a's will cancel each other out, or 1 minus 1 is 0. Anything to the 0 power is 1, and I don't have to write that. Next, we have a b squared on top. Notice there are no b's on the bottom, so there's nothing to subtract, so we're going to have b squared that's going to stay in the numerator. Finally, we have c cubed over c squared. 3 minus 2 is 1, so we have c to the first, or just c. So our simplified answer is b squared c. Example 9, we have a squared over a. So 2 minus 1 is a to the first, or just a. Then we have c cubed on top over c to the fifth. Well, if we subtract numerator minus denominator, 3 minus 5 is -2. So we get c to the -2nd power. But remember, for our rules for simplification, we cannot leave a negative exponent in our answer. How do we get rid of negative exponents? We move them to the denominator and they become positive. So the a stays on top, and the c to the -2nd becomes c squared on the bottom. So here's the first example where we actually had more c's in the bottom to begin with, so notice where the c's end up in the answer, also in the denominator. That's because we would have c times c times c on top, we would have 5 c's on the bottom, and if we start canceling, notice that the 2 c's left over are in fact in the denominator. Here's another example 10 here that gets a little more complicated. We want to clean everything up where we can. We need to do some canceling with coefficients. There's multiplication that's occurring on top. And really you can deal with this one of two ways. I like to multiply everything together on top. Then I'm just dealing with one coefficient in a set of variables. So if I clean up the top, I need to do 5 times -81. That's going to give me -405. Then I have y squared times t to the 4th. I typically write my variables in alphabetical order, so t to the 4th y squared. It's all still over 45t cubed. Now we need to simplify. We can deal with the coefficients first, but we need to reduce if we can. The first thing I checked was to see if 45 goes into 405, and in fact it does. So 45 goes into 405 9 times, so that leaves you with a -9 on top and a 1 on the bottom. We don't have to write the 1 on the bottom. So now let's deal with our variables. We have t to the 4th on top, t cubed on the bottom. 4 minus 3 is 1, so that'll give us t to the 1st on top. We also have a y squared in our numerator with no y's in the denominator, so nothing to subtract or simplify there. So our final answer is -9t y squared. Number 11, we have -3x cubed y to the 4th over -2x squared y squared. So as we look at those coefficients 3 and 2, hopefully you're recognizing that those do not reduce. However, they are both negative, and whenever you have a negative in the numerator and a negative in the denominator, we simplify that by making the answer positive. So essentially these negatives cancel each other out, and our final answer will be positive. We will still have a 3 on top and a 2 on the bottom because 3 over 2 does not reduce. Then we have x cubed over x squared, so 3 minus 2 is x to the first. And we have y to the fourth over y squared. 4 minus 2 is 2, so that will also stay on top, y squared. So our final answer is 3x y squared all over 2. The next property is called the positive power of a quotient property. What this says is that if you have a quotient raised to a positive power, it equals the quotient of each base raised to that power. Remember, a quotient is a fraction, or division. So we have a over b, and in parentheses, that entire fraction is being raised to the m power. So what that means is it equals a to the m over b to the m. Essentially, everything inside the parentheses, numerator and denominator, takes that exponent m. In the example, we have 3 over 5, and it's being raised to the 4th power. So that's 3 to the 4th over 5 to the 4th. 3 to the 4th is 81. 5 to the 4th is 625. You always need to make sure that your fractions are simplified, and one trick is that if the fraction is initially simplified, when you multiply it out, you won't be able to simplify here either. So notice that 3 over 5 is in simplest form. That also means that 81 over 625 is in simplest form. So that's something to remember. So let's look at some examples. We have 2/3 raised to the 4th power. Well, that's 2 to the 4th over 3 to the 4th. 2 to the 4th, remember it's 2 times 2 times 2 times 2, which is 16, over 3 times 3 times 3 times 3, which is 81. Because 2/3 does not simplify or reduce, neither does 16 over 81, and we have our simplified answer. 13, we have 6 over 2 raised to the 3rd power. And you have an option here. You can simplify inside first if you'd like, or you can apply the property and then simplify at the end. Personally, I think it's a little easier to simplify first since we're dealing with smaller numbers. So 6 over 2 becomes 3 over 1, still raised to the 3rd power. You could also write it as 3 to the 3rd. Remember, we don't typically write whole numbers over 1. So this becomes 3 to the 3rd over 1 to the 3rd, or 27 over 1, or 27. On the bottom, 3 to the 3rd is 27, so you can see you come to the same answer. If you had not simplified first, the other option is 6 to the 3rd over 2 to the 3rd. 6 to the 3rd is 6 times 6 times 6, which is 216. 2 to the 3rd is 8. Now this does need simplified. You can see that they're both even, so definitely a 2 goes into both of them. But if you tried a larger number, like let's say 4, 4 also goes into 216, but so does 8. So if you reduce them both by 8, you also get 27 over 1, or 27. So you can see there are multiple ways to solve the problem, but I think that simplifying first is the easiest. Example 14, we have x cubed over 2 to the y power, and it's all being raised to the 2nd. Here's the first case that we see where we've got exponents inside and outside. But remember from our multiplication properties that if you have a power raised to a power, we multiply the exponent. The new property we just learned today says if you have a quotient, like x cubed over 2 to the y, they both are going to get this 2nd power outside. So we have to do some multiplication. X to the 3rd squared, you could write it like this, and on the bottom we have 2 to the y also being squared. Or you can skip this step, and most of you will be able to do that after a few examples. We get x to the 6th over 2 to the 2y. Be careful here, it's multiplication. 2 times y is 2y. You could write y2, but typically we write our coefficient in front of the variable. This cannot be simplified because we don't know what y is in the bottom. We can't simplify that 2 at all. We also don't have any subtraction. We don't have like bases anywhere, so this problem is finished. On 15, we are going to multiply the 2 times 4 to get c to the 8th over, same thing on the bottom, 3 times 4, d to the 12th. We don't have like bases, so we can't simplify any further. Now let's look at some examples where we have scientific notation. This is a lot like the scientific notation for multiplication, except we're going to apply the quotient rules as opposed to the multiplication rules. Remember, the quotient rules say subtract exponents on like bases. So remember with multiplication, we actually multiplied the numbers out in front. So here we're going to divide 3 divided by 6. Well, that's a half or 0.5. I'm going to use the decimal here because I know it's scientific notation. We don't typically write scientific notation, or we don't ever write scientific notation using fractions. Then I need to subtract my exponents. So then I get times 10 to the 4th. But remember, we always want our answer in proper scientific notation. This number here needs to be greater than or equal to 1, and it's not. I need to move my decimal 1 place to the right. That's going to give me 5 times 10. And do you remember the rule on the exponent? I made the number larger, so I need to make the exponent smaller to compensate for moving the decimal. 17, we have 2 times 10 to the 8th over 8 times 10 to the 3rd. 2 divided by 8 is a 4th, or 0.25. When I subtract my exponents, 8 minus 3, I get times 10 to the 5th. But again, we're not in proper scientific notation. We need to move the decimal 1 place to the right. And to compensate for that, we need to lower our exponent by 1. So we get 2.5 times 10 to the 4th. We learned 2 properties today, so hopefully you're able to apply both of those properties to evaluate and simplify the expressions, and that all of the examples make sense. Remember, if something is troubling you or you have a question somewhere, to make sure that you ask about that in class. We will work on worksheet 7-4A.